Okay. Oh. All right. All right, let's get started. Okay, so I think what I'll do for attendance today, given the accident and whatnot, is anybody that's not here, I don't know if we'll see what happens with the emails after this, but I'll try and be gentle as possible. Okay, all right, so as of now, on Blackboard, everything should be current, okay? So you all should have a general idea of where you are in the class in terms of grade-wise. Keep in mind there's a couple of, so let's talk about what we have left in this class, okay? Because we are down to the wire, I mean, you can see. So I'm assigning homework 8.3 today, okay? So we have a homework 8.3, 8.4, 8.5, okay? That's our three remaining homeworks on influence lines. We have two homeworks on matrix analysis, 9.1 and 9.2, okay? They will be worth a little bit more, but you'll be given a lot more time to do those. So 9.1 and 9.2, okay? Obviously we have attendance and whatnot, but the only two things that are left over is the project, okay? The second submittal for the project, which is due next Friday at 5 p.m., right? Not like 4 days from now, we're talking about 11 days from now, right? 2 weeks, almost 2 weeks from now. And then we have the final, and that is CE 312 in a nutshell, all right? So in terms of where you are at in the class and whatnot, there you go. Here in a little bit, probably like sometime next week, I'll send out my at-home game spreadsheet. Y'all remember what I'm talking about? That's, if you don't know what I'm talking about, a buddy of mine in grad school, he would call it playing the at-home game, where he would take his attendance grade, his homework, his exam 1, exam 2, and sort of figure out what he needed to get on the final to get an A or a B in the class. Call that playing the at-home game. So I have an at-home game spreadsheet that you all can mess around with if you would like. I do round, by the way. So if you get an 89.7, that's an A. I round up. So there's that. Oh, I do have one bonus assignment for doing the course evals, which we'll do during pre-finals week after you come back. Sound good? All right, the only other thing I wanted to mention is steel design. How many of y'all are planning on taking it next semester? Okay, just so you all are aware, there is no textbook for the class. I do not make you buy a textbook, but you do have to get the manual. You really can't do steel design without the manual. Now, the way that it works is if you were to buy the manual on your own, it would be like $400. You're not doing that, right? So the way that the steel manual works is there's a university discount program where the professor goes on to AISC and requests a coupon code, and then you purchase the manual at something like $125 as opposed to $400. I've requested the coupon code. It hasn't come in yet, but what I'm going to do is I'm going to distribute that based on who's registered for the class. So I'll send a note out with information on how to get the code. Once you've registered. So if you're thinking about taking steel design but you haven't registered, register, because I'm not going to know who's in the class without that, okay? Sound good? Everybody get the code. All right, okay, so with that, let's go ahead and jump into influence lines. Okay, I don't know what's going on with that checkout thing, but we'll just ignore that. Okay. All right, so let's recall the Mueller-Breslau principle. So we are still using the Mueller-Breslau principle to construct influence lines. So what we're going to be doing is identifying a response of interest. So it could be a support reaction, it could be a shear in moment at a given point, etc. We will then move that structure through a unit displacement, and then the resulting deflected shape is the influence line. Up until now, what we have done is influence lines for reactions, and we have done influence lines for internal shears and moments, which, by the way, how was the last homework? Was it straightforward? Everybody good with that? Okay. Did you have a question?
Well, I wanted to know an answer, but you probably can't say that.
Well, we'll look at it here in a bit. Okay. All right. Now, one of the things that we have not discussed yet is a fixed support. Okay. I want to be clear that none of the rules that we've derived so far are invalid for fixed supports. If anything, they are explicitly valid. But Because of that, you need to be careful on what you're doing and why you're doing it. Okay? So I want to make a point. Okay? So let's say, for instance, that we are constructing an influence line, and we are constructing an influence line for the vertical reaction at support A. So let's say I have a structure, okay, and I want to find the influence line for this, okay? So remind me how the Mueller-Breslau principle works. I remove from the structure the ability to resist AY. I move it through a unit displacement, right? Okay. Now, here's the thing. What we're going to do is we're going to move the support through a vertical translation, okay? I didn't say anything about moving it through a rotation, okay? So, take a look at this. If you're constructing your influence line and you do this, that's wrong, okay? Okay, so notice how what I'm doing is I'm lifting the support, but I'm sort of like lifting it like this. That's wrong. Because what's happening right here is you're not only translating it, but you're rotating it. I didn't say we're rotating it. We're moving the structure through a vertical translation. Because it's a fixed support, it doesn't rotate. So this is wrong, that's correct, okay? We pick the whole structure up, okay? Does that make sense? And I'm giving you the Mueller-Breslau explanation as to why an influence line would look like that. Okay, I'm going to follow this up with a statics example or a statics explanation as to why this doesn't work. By the way, this also works for moment reactions. For moment reactions, we would rotate, but we wouldn't translate. Moment reactions are a little easier, I think, to conceive of than vertical reactions, which is why I have a slide devoted to that. Okay, so what we're going to do is a simple cantilevered beam example. We're going to draw the influence lines for this structure for the following responses. Okay, so we're going to draw the influence line for the reaction at A, both reactions at A, I guess you should say, and then the internal response at B. Okay? All right. And by the way, this is a really simple example. I'm going to show you what happens if we take this beam and run wild with it. Like what would happen if we had a really, really weird support scenario for a fixed-ended beam. And then you'll kind of see it's actually not that bad. It's actually pretty easy to reason through. Okay? So, okay. All right. So what we're going to do here is we're going to draw an influence line for two reactions. Okay, so let's draw the influence line for AY, and then let's draw the influence line for MA. I'm going to have something to say specifically about this MA influence line here in a bit, but just bear with me. Okay. All right. So, again, as I said, if we pick point A up and we move it through a unit translation and rotation, that's wrong. Okay? So, here's what we need to do. Okay, so we're drawing the influence line for AY. So let's do the Mueller-Breslau first. Okay, so I'm going to take point A and I'm going to move it through a vertical translation, but I'm not going to rotate it. What does the beam look like after I've done that? If I pick point A up, pick it up one, but I don't rotate it, what would the beam look like after that displacement? Keep in mind, by the way, influence lines don't curve. So how do I pick point A up one without rotating it? What does the beam look like after? Say it again. That's 100% right. I'm just picking the entire beam up. Okay? I propose that the influence line for the reaction at A is just this. So 0 here and 1 here. That I propose that the influence line for the reaction at A is a constant value of 1 across the entire structure. Okay? Now, some of you are probably maybe like, I don't know, maybe having a hard time visualizing that from a Mueller-Breslau standpoint, and I can understand that. Instead, I want to give you another way of thinking about it. Okay, so remind me, before we got to the Mueller-Breslau principle, how did we construct influence lines? Like, ignore all this, pick the structure up and move it through a displacement. I mean, what is the definition of an influence line? It's a diagram that tracks the response due to what?
Unit displacement.
Not a unit displacement. I'm saying the moving one kip load across the entire structure, right? That what we're doing when we draw an influence line is we take a one kip load and we move it across the structure and then we record the response. Does that make sense? Everybody okay with that? Okay, so here's my point, okay? Let's consider the following structure. Okay, so here's the structure, and I have AY MA, okay? And the beam is 20 foot long. Is that how long the beam is? Okay. I want to place the load right there. Okay? What is AY in this scenario? What is AY? 1. Does everybody see that? Sum of verticals, 1 down, 1 up. Okay? All right. So, okay, now let's place the load right here. It's right smack dab in the middle. 10 foot over, 10 foot over. What is AY? Interesting, right? So in fact, what you're telling me is that does it really matter where I place the load? Isn't the vertical reaction 1 everywhere? Does that make sense? So could I do this? Could I basically say, could I maybe, I don't know, derive an equation where I say, okay, this is 1.0 where that's x? And couldn't I say that if I could get that? That no matter where I place the load, AY is 1. I mean, that's the graph of that equation, right? Y equals 1. Make sense? Okay. So if that's the case, let's sum moments at A. Okay? And what happens when I sum moments at A? I have 1 times x, and then I have MA, right? So I've got, what do I have? I have MA. So, I mean, what am I going to have? I'm going to have MA equals x. Interesting. Okay. By the way, so, okay, hold on. Let's think about this. How would I graph MA equals x? How does that graph?
Just a straight line.
Straight line going like that, right? With that being 0, right? Okay. 0 and 0. And by the way, what is the value like right here? 20. Okay. Now, a couple things worth mentioning. It is typically conventional to put a sign convention here for your influence line. Like, we haven't really been bothering with it with vertical influence lines. Like, it is customary to sort of ignore it for that because vertical influence lines, like, they're sort of always treated upwards. But moments, like, I will say that you will have some engineers draw their moment influence lines like this. Some of them draw it like that. I'll be honest, I probably draw it downwards. Okay, and I'll tell you why. Because if I place a vertical load on this beam, no matter where I put it, it's going to cause the beam to frown at you. So I will probably draw the influence line negatively, but it doesn't really matter as long as you report your associated sign convention. Does that make sense? And what does this also make sense physically? Okay. Well, what this is saying is that the further this gets away from MA, the more moment resistance you need at the fixed support, which hopefully I would think makes sense, right? So far, so good? Okay. All right. Any questions on this? Okay. Okay. Now, by the way, before we move on, let's consider the following example. Okay? I'm going to get a little wild with it. Okay. That's kind of nuts, isn't it? That's a weird structure. Okay? We're going to draw an influence line for AY. And just to put some simple dimensions on this, and my apologies that this is nowhere near to scale. Let's just assume that these are all 15 feet. By the way, is this structure, what's the IE value for this structure going to be? Now, before you start counting stuff up, let me give you a different way of thinking about it. All right? What is the IE for this structure? Like, is this determinant? It's not? All right, hold on. Let's go back. IE is R minus EC plus 3, right? This has 1, 2, 3 reactions, no hinges, right? Everybody with me on that? Now, what I did to this beam is I basically said, okay, I'm going to add a roller, but I'm also going to add a hinge. So is this structure determinant? Yes. We're going to add a hinge, add a roller. Add a hinge, add a roller. So is this determinant?
Yes.
So it is, right? So these are all going to be straight line segments on the influence line. Again, this one's kind of a crazy influence line. But I want you to see that this is very within our wheelhouse. Okay. So how would we draw the influence line for AY? So how do we do this? We take this point and we move it through a unit translation, right? But we don't rotate it, right? Fair? Okay. So that means that this point right here has to be 1.0, right? By the way, what does it have to be? What does the influence line have to be here, here, and here? Like, what's the influence line have to be right there, and right there? If it's an influence line for reactions, what's the rule say? 0. So maybe the influence line should do this. Straight line. Boom. 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 Right? Rigid lengths. And then whoop, right? So this is going to be 1. And since all these are 15 feet, 0, -1, 0, +1, 0. Is that fair? I mean, does that seem incredibly challenging? You tell me. We're moving point A through a unit translation, but it's not rotating. But the hinge serves to change the rotation, and then the supports serve as the fulcrums on the seesaw. Okay? Everybody with me on that? Okay. I just wanted to do this problem on the side because I don't want any homework or exam problem to go, well, Dr. Mike did this really simple problem, but then he didn't do something that was really difficult. So, okay. Sound good? Okay. Let's get back to this problem. Because I want to talk about this, and I want to talk about the internal shear and moment at B. Okay? Okay. So here's the beam. Okay. And this is point B. Okay? Now, before we start drawing these influence lines, I want to have a thought experiment with you all because I want to see if this makes sense. Okay? Now, I know this isn't a fixed-ended beam, but just bear with me. Okay. Let us say that this is a diving board over the water. Okay? And so how does a diving board work? You walk out here, you jump, boom, go down here, right? So if you were standing right here, that would be the worst case like bending type scenario you could think for the diving board. That's really going to make the diving board want to flex, right? So let me ask you a question. Let's say that you're standing right there. Okay? Does the diving board flex any? Well, I mean, it flexes, but not as much, right? Let me ask you all a question. Let's say I'm standing right here. How much shear and moment is going on right there? If I'm standing here, how much shear and moment is going right here? Think it through. It sounds like a trick question. I'm not trying to trick you. Like if you're standing there, think physically what's going to happen to the diving board. It's going to just go along for the ride, right? Is the diving board experiencing any flexure or any shear out there?
Zero.
Zero. Okay. Okay. So here's my point. Let's draw the influence line for shear at B and moment at B. Shouldn't it be 0 from here to here? I mean, why would point B experience any flexure if the load is back here, right? The load's back here, it's just going to go along to the right. Okay. Does that make sense? All right. Now, I can already anticipate some confusing thoughts about the Mueller-Breslau principle. So let's take the Mueller-Breslau principle. So let's take the shear at B. So what am I going to do? I'm going to, here's the beam, right? I'm going to install a shear release right here, right? And so some of you are going to tell me that this side has to go down, this side has to go up, and that's got to be what the shear influence line looks like, right? That's what y'all are going to tell me, right? Okay. Now, I was very choosy in my language on Friday. What I said was this. I said that whenever you install a shear release, this side tends down, this side tends up. I didn't say it goes down or goes up. I said it tends down, tends up. Has a tendency to go down, has a tendency to go up. Okay. I was being very choosy with that. Okay, so let's revisit shear influence lines. Okay, so what do? You remove from the structure the ability to resist shear at this point. You then move it through a unit shear displacement. So what do we know about that unit shear displacement? This side tends down, this side tends up, right? What do we also know about the shear displacement? What's that total jump got to be? 1. Okay, but here's my problem. Okay, my problem is that if this left side, that is the worst curly brace ever. If that left side were to drop downward, I still have a fixed support right there. So the only way that that can work is if it bends. Influence lines don't bend. Okay? So my question is, if this has got to remain flat because it can't bend, this side tends down, this side tends up, total displacement of 1, the only way I can do that is that. That is the influence line for the shear at B. Okay? And if you're having a hard time visualizing that, let's think of another way of looking at it. All right? What did you all tell me that if you put a vertical load going down, that this reaction is 1.0 regardless of where that is, right? So let's cut a section at point B. If the load is on the left side of point B, what's going on inside the section? What happens if I look to the right? Do I see anything on the beam? Nothing. So anything where the load is to the left of B, there's no shear. But what happens if I take this load and what happens if I just scooch it? Happens if I just scooch it over here. I don't know why I didn't want to grab the arrowhead. What happens if I scooch it over there? Now, if I cut a section and look to the right, I have a sudden increase in shear, right? Once the shear hops onto that other end of that section cut, I suddenly have a total jump in shear of 1. Does that make sense? I also propose that in order to draw the influence line for moment at B, we're going to put a hinge here and undergo a unit rotation, okay? Now, if I put, let's just think about this. What's the structure going to look like if I put a hinge right there? Like in real life, what would happen to a cantilever beam if I put a hinge right there? What would it do? Like here's my cantilever beam, I stick a hinge, and I just say, all right, here you go, what's the beam do?
Swing down.
Right? So the influence line for the moment at B is like that. The slope of that line is 1 because it's a unit rotation. And so if you go over 10 feet, minus 10. Does that make sense? That, ladies and gentlemen, is the influence line for the shear and moment inside a cantilever beam. All right, does that make sense? Okay, can I show you trusses real quick before we call it? I'm not going to make you do a truss, by the way, but I do want to show you what's going on. Everybody good? All right, let me show you a truss real quick. So what we've been talking about with influence lines for beams, for supports, and so on and so forth is that the Mueller-Breslau principle will make our life a lot easier. Now, I want to be crystal clear from a theoretical standpoint. There's nothing to say you can't use the Mueller-Breslau principle for trusses. It would just, in practical terms, it would be impossible to apply, because if you wanted to draw the influence line for the internal force in a given truss member, you would have to remove that truss member, put it through a unit displacement, and then figure out what the truss looks like afterwards. That would be impossible. And so the only real way to effectively draw an influence line for a truss is by brute force. So just move the load, solve the truss. Move the load, solve the truss. And so it's kind of a pain, but you can do it. Really the only thing that I think is worth discussing with truss influence lines is, do you put the load, like when you move the load across the structure, do you put it on the bottom joints or do you put it on the top joints? Okay? And my answer to that would be, where's the road? I mean, I know that might seem like a facetious answer, but in all honesty, influence lines are meant to assess a moving load. So put the load where the load's going to be. So for example, for this truss over here on the right, I would not hang the loads along the bottom of the truss. I would put it on the top because that's where the road is. Right? Does that make sense? Everybody okay with that? So just to show you how this would work, if I wanted to draw the influence lines for this truss, so a couple things to keep in mind. So what we would have to do is we would have to solve the truss, I guess like theoretically 5 times, because what we would do is put the load here, put the load here, put the load here, put the load here, put the load here. But there's a couple things that we can do. First off, if I put the load at A or E, okay, what is the internal response inside the structure? What? Okay, you had a very good answer that's going to affect B and D, just reverse. But I'm talking about if I put the load at A or E, what's the internal response inside the truss? It's 0, right? If I put a load at A, the truss isn't seeing anything. If I put the load at E, the truss isn't seeing anything. So really, I only have to solve the truss 3 times, and if we're being honest, I only need to solve the truss twice. Because if I solve the truss due to the load at B, I could just mirror my results, and that's the answer for the load at D. By the way, I can still use the influence lines for reactions. I can still do that. So like this is the influence line for AY, this is the influence line for EY. I can still do that. There's nothing to say I can't do that. So let me show you what I did here. So what I did is I put the load at point B, solve the truss, put the load at C, solve the truss. If I wanted to put the load at D and solve the truss, all I would do is just take this and like flip it like that. And so I really have all my influence lines solved. So if you want to draw a given influence line, what you would do is just pay attention to a given member. So like when the load's at A, let's take member AB. When the load's at A, this is 0. When the load's at B, this is 1. When the load's at C, this is 2/3. Does everybody see that? So when the load is at D, it's going to be 1/3 because it's going to be that mirrored response. And when the load is at E, it's 0. So all you do is you just record all your responses, put it in a nice little table, and plot it out. And so typically when you draw an influence line, you take your tensile results as positive, your compression results as negative, and here's what you get, okay? So here's some influence lines. So for example, let's see if we can investigate some patterns, okay? So what about the influence line for member AB and member CD, okay? So member AB and CD, that was, you know, this member and this member. Those are both in tension. Why are they totally, like, why are the influence line values all positive? Because it's on the bottom of the truss. And so if you can think about this like a big old beam, like the top side is experiencing compression, the bottom side is experiencing tension. That's basically what we've got going on. Remember, FG was on the top. So all of those are in compression, right? What do we have going on here? Remember CF. Remember CF was an internal diagonal. So it sort of flips from tension to compression when the load moves over. And then member BF. So member BF was a vertical member. So what happened on this truss is when the load was right here, it was 1, but when there wasn't a load here, this was a 0 force member. So the only time member BF experiences a load is when there's a load right at B. Okay, does that make sense? Everybody, I mean, I know I kind of threw that at you, but it's really all you do is just brute force it and plot it. It's really not that hard. So, sound good? Okay, I'm going to pull up the code one more time. I will see you all on Wednesday. We're going to start applying influence lines then.